Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemets. And without any further ado, let's look at this question that we have here. Okay, so we have question 6 still on chemical equilibrium. It says a steam H2O in gaseous state reacts with hot carbon, which is carbon in a solid state. Remember, if we have any substance in solid state, we say it won't be included in the Kc expression because the Kc expression only considers concentrations of aqueous and gaseous substances, right? Then, okay, this is happening at 1000 degrees Celsius according to the following balanced equation. Then we can see that balanced equation there with all these other substances in gaseous state, but only the carbon is in solid state. So note that this will not be part of the Kc expression. Now, initially 36 grams of steam and a certain amount, so certain amount means X amount, and then of carbon was or were placed in a 2dm cube cell container and allowed to react. At equilibrium, it was found that the amount of carbon changed by 0.225. Note that statement. At equilibrium, it is found that the amount of carbon changed by. So this does not mean that at equilibrium we find 0.225 mole, but rather that at equilibrium, we observe that the change in the number of moles was by 0.225 mole. So in order to find the number of moles of at equilibrium, we do understand that we need to take this certain amount of gas or this certain amount of carbon, because we are talking about carbon, not the gas. Okay, so the solid. So we need to take this certain amount of carbon, subtract by 0.225 mole, and then we get the number of moles at equilibrium. So note that statement. So that means the 0.225 mole here is supposed to go to the change block instead of the equilibrium block. Okay, so, but then we'll get to that in a few, after giving out the definition for dynamic equilibrium. So what is the definition? We say it's when the rate, so this is a state in our chemical equation where the rate of the forward reaction is equal to the rate of the reverse reaction, right? Okay, so let's now proceed. 6.2 says calculate the equilibrium constant, Kc, for the reaction at 1000 degrees Celsius. So we know the first thing that we need to do is obviously have our, so now let's begin. For our ratios, remember here we have our 2H2O, and then here we have our carbon, and then note that it's a solid, and then here we have 2H2, and then here we have carbon dioxide. Now if we have to drop the coefficients for our ratios, we have 2. Coefficient of carbon is 1, coefficient here is 2, and then coefficient here is 1. Right, so that's what you do for the ratio block. And then initial, we are given that initially 36 grams of steam. But then remember here we have initial number of moles, not initial mass. So what we need to do is calculate the number of moles of steam. So number of moles of H2O would have to be mass over the molar mass. Now the mass is 36 and the molar mass of H2O has to be 2 plus 16, which is 18. Now 36 divided by 18, this should give us 2 moles, right? And then what do? We put our 2 in here, right? Now, what else are we told? And a certain amount of carbon. So certain amount means X amount. So we're going to put X here. But then if we are saying that only the 36 grams of steam and a certain amount of carbon were placed in a 2dm cube container, and then they were sealed there, that means at the very beginning, we only had the reactants and a 0 amount of products, right? So, because at the beginning, we only had those 2 reactants. So no products were formed yet. So that is 0 and 0. Okay, but when we read further, they say at equilibrium, it was found that the amount of carbon changed by 0.225 mole. Note that it changed. So that means on the carbon, for change, we're going to put 0.225. So that means to find the one at equilibrium is the initial minus the change. Now remember, from here we are getting that the forward reaction is favored. So forward reaction is favored. Why do we say forward reaction is the one that will be favored? Because we are trying to use up this reactant in order to form the product. So always we know that the reaction that promotes the forming up of product is the forward reaction. But then remember, what did we say? If the forward reaction is favored, then we must subtract on the reactant side by saying I minus C is equals to E. But we must then add on the product side, because as we are using the reactant, we are forming up the product. So it's I plus C is equals to E. So for both these reactants, I will have to subtract, but then for both this product, I will have to add. But before I do that, I need to find the values in here. Now, how do I find the values in here? You will remember that I said the change block relates to the ratio block. If you want to find the number of moles of the other substances while you already have the number of moles of one of the substance there, then you need to use the ratio for the others, right? Now, if we can just quickly do this, this is 0.225, but then carbon shares the same molar ratio with carbon dioxide. So that means for every 1 mole of carbon that is in reacted, then that means there is 1 mole of carbon dioxide that is produced. Right, so that means even the number of moles will be the same here. So that means we are going to have 0.225, right? So same ratio means same change in the number of moles, right? So for the same amount of moles that are being used up here, then the same amount of moles are being made up or produced on carbon dioxide. Okay, so now we have that, but then looking at this 2 here, it has a ratio of 2. So how do we find the number of moles here? It's simple. We just simply take this one, cross multiply with the 2. So 0.225 multiplied by 2, then divided by 1. Now, obviously, the ratio is telling us that for every 1 mole of carbon that is reacted, there is 2 mole of steam that needs to react as well. So if we have 0.225, then that means we need 0.45 moles to react with that carbon. And then again here, for every 1 mole of carbon that is being reacted, then there is 2 moles of hydrogen gas that is produced. So that means also again we'll have 0.45. And then as you can see here, these ones, they share the same ratio and they also have the same change in moles, right? Okay, then we get to this part. If we want to find the number of moles at equilibrium, note for the reactants we have to subtract, and then for the products we have to add. Subtract on the reactants because we are using up the reactants. Add on the products because we are forming the products. So that is 2 minus 0.45. We get 1.55. And then here, there will be x minus 0.225. So which is obviously x minus 0.225. Okay, and then for this part here, note that after this line, we are now dealing with the products, right? So these are products. Then we have to say 0 plus 45, which is 0.45. Then 0 plus 0.225, which is 0.225, right? Now to get our concentrations, we go back here and read. They say these were placed in a 2 dm cube container, right? So always note your volume will be given in the statement. So now if we have to divide, we have to divide all of these numbers here by 2, remember. So that's 1.55 divided by 2. So you're going to use your calculator for that. So 1.55 divided by 2. And then you obviously have 0.775. And then for this one here, remember for concentration, we said we only focus on the substances that are in gaseous state and also in aqueous state. So we do not really care to find the concentration of this, because after all, it won't be included in our Kc expression. So we might just as well leave it like that because it's in a solid state. So the concentration there is just constant throughout. So now let's get to this one. 0.45 divided by 2, we get 0.225, right? So that's 0.225. And then if we say 0.225 divided by 2 for the last block, this one here we have 0.1125. Now at this point, we can now calculate our Kc, right? So now in order to calculate Kc, we now need to say Kc is the concentration of the products. So we have our product is carbon dioxide. And then as we can see, the ratio here is 1. So it has an exponent of 1. We can just leave it like that. And then we have multiplied by the concentration of hydrogen gas, which has a ratio of 2, which becomes an exponent like that, over the concentration of the reactants. So the only reactant that we are going to put in there is H2O, because the other reactant here is a solid and does not make it to the Kc expression. Then this is H2O, and then here we have a square because of the ratio here. Now all we need to do right now is substitute in our values. So for carbon dioxide we had 0.1125, and then for our hydrogen gas, we have 0.225, and then square that over the hydrogen, the H2O mean steam, 0.775, and then square. Now at this point, you only need to punch in your calculator, and then you find that your Kc is equal to 0.009, right? So 0.009, and then that's how you get that one, right? So obviously, if you had got it in terms of your scientific form, then you would have 9.48 times 10 to the exponent of negative 3, right? So either way, it would have been correct, right? So whether you wrote it in normal form or you wrote it in terms of your scientific form, right? Also, again, if you wrote everything here, then it would be 0.00948. And then both these Kc values are correct. It's just a matter of one is in normal form, decimal form, and then the other one is in scientific form, right? Okay, so that's how you could have calculated your Kc there. Let's now proceed. Now, 6.3 says the graph shows how the rate of the forward and reverse reaction change with time. Now, 6.3.1 says give a reason why the rate of the forward reaction decreases between T0 and T1, right? Now, obviously, we know that if our forward reaction is decreasing, it only means that it's because the reactants are being used up. Remember, the forward reaction promotes the using up of the reactants in order to form the product. So, which is why every time you are looking at our graph initially for the forward reaction, we always see it decrease here, because remember, initially the reactants will be used up. So it's because reactants are being used up, right? So the reactants are being used up. Now, to be more specific, we can say it is actually the steam H2O. So H2O is being used up, right? And then, okay, let's now proceed. We have 6.3.2. What change was made to the equilibrium mixture at T3, right? At T3, we can say that both the forward and the reverse reaction are increasing like that. And then we always know that if we find both the forward and the reverse reaction increasing just like that in this manner, the only factor that was done there is adding a catalyst. So we always know once we have this change here, or we have something like that, then the change that occurred is that there was an addition of a catalyst always. So this is based on your notes. And then at time T2, the temperature of the system is increased. Is the forward reaction exothermic or endothermic? Right. Now let's understand this. Let's understand this. They say the system the temperature of the system was increased. So before we can really answer that, let's break down what we know according to our Lee-Chatlas principle. Number one, we know that an increase in temperature always favors, so an increase in temperature favors the endothermic reaction. So it doesn't matter whether your endothermic is forward or reverse. An increase in temperature just simply favors the endothermic reaction. Now, from here, from looking at what happened at T2, let's now focus our attention on time T2. Time T2 is telling us that the reverse reaction is the one that is being favored, because we can see a gradual increase on the reverse reaction, but then a gradual decrease on the forward reaction. So obviously this is telling you that the reverse reaction was the one that was being favored, while the forward reaction was not favored. So we wanna state that observation there and say at time T2, the reverse reaction was favored. Now note this. If we are saying an increase in temperature favors the endothermic reaction, and then we find that at T2, the reverse reaction was favored, then this means the reverse reaction is endothermic. The reverse reaction is endothermic. But then remember, they did not ask us about the reverse reaction. They asked us about the forward reaction. Now, we do know that if the reverse reaction is endothermic, then it goes without saying the forward reaction is exothermic. Thus, the forward reaction is exothermic. So as much as that was just for 1 mark, you can see that there was a lot of thought process into it. So the forward reaction is exothermic. Then we have our exothermic. Now, if it wants you to refer to the Lee-Chatlas principle to explain the answer to question 6.3.3, now you have your explanation. An increase in temperature favors the endothermic reaction. At time T2, we saw that the reverse reaction was favored. That means the reverse reaction is endothermic. Thus, the forward reaction is exothermic. So we can use that as an explanation to 6.3.4, right? So that's how you could have went about answering that question. So please press that thumbs up button if you've enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.